Hey, and welcome back to today's videos. Today we're going to talk about vector fields, and we're going to start talking about integration over vector fields in that context. The basic idea of a vector field is that sometimes you want to describe a function that does not only have a magnitude, but also a direction. The prominent example for this from physics or from engineering is any kind of force. Whenever a force attacks at a certain point, that force is characterized by a direction and the magnitude of that force. So the natural way to express that is through a vector. And if that force changes with the location, then we can express that as a function that assigns to each location a certain vector. And functions like this are called vector fields. They have some special properties, and we'll have to talk about integration over vector fields. And that's going to be the topic of this video and the next couple of videos. So today we're going to start section 15.4, vector fields. And integration over vector fields. As I said, the goal of this whole thing is to describe forces that have a value, a magnitude, and a direction. Forces with magnitude and direction. That change depending on the location. So depending on the point in the plane, in space, or even generally in some n-dimensional space, like for example in 4-dimensional space-time. There's lots and lots of examples of vector fields like that. One possibility would be winds. So imagine you're planning the route for an airplane that follows a path through 3-dimensional space around the Earth, and that is affected by winds. Of course, the wind changes depending on the location. So the classical way to model this would be to model the winds as a vector field and then the path of the airplane as a curve through the space. Okay, so one example would be varying winds in the atmosphere. And of course, that is not just important for planning the path of an airplane, but also, for example, for the weather forecast. Or imagine something like swimming through an area that has currents in it. And you also want to know how much energy you have to spend, or maybe you want to know where a particle floats. Let's say you have lost something in the ocean, and you want to know where it ends up. Then you want to know how that thing moves depending on the currents that you have, and you would model those currents through a vector field. So currents in the sea. That would be another example. Of course, the gravitational field of the Earth is also an example for a vector field, right? A force that acts on a particle, on a body in that gravitational field is dependent on the location, of course. So, for example, the movement of a satellite under the influence of Earth's gravitation. Earth's gravitation could be modeled as a vector field. And finally, one class of examples that often comes up in engineering is the movement of a charged particle through an electric or magnetic field that influences its movement. So the electric or magnetic field is then also modeled as a vector field. Okay, let's start with the definition of a vector field. Formally, that's not hard to define. We have one prerequisite to make things a little easier. We'll only define vector fields on connected sets. And we'll call a set connected if any 2 points in that set can be connected by a curve that is completely contained in that set. You may remember our definition of convexity that was somewhat similar to that. For convexity, we required that any 2 points in the set can be connected by a straight line that is completely contained in the set. And now for connectedness, that is a weaker version of that. We don't require the connection to be a straight line anymore. It just needs to be a continuous curve. Okay, so that's what we call a connected set. And that is the natural domain for a vector field as we want to use it here. So let's define that first. A set D, subset of R to the n, is called connected if for any 2 points x, y in that set D, there is a continuous curve with endpoints x and y that is completely contained in D. So for a quick illustration, for example, any convex set is naturally a connected set. You can even connect any 2 points by a line. So a set like this, that would be connected. But it doesn't have to be convex. For example, you could also take a set like this. That's far from being convex, but it's still connected. On the other hand, a set like this will not be connected. Yeah? So those both parts make up the set D that is not connected. And of course, it's totally fine if the set has holes in it. Yeah, like for example, take a set like this here, and then cut a hole in it or two, so that the set that we're talking about is actually this here without the holes, right? So that's also connected. Okay, so that's the natural domain for a vector field. And let's define what a vector field is. So that's part 2 of that definition. Let D be a subset of R to the n, and let that be connected. Then a function, I'll usually call a vector field V, but of course that is totally arbitrary. A function V defined on R that maps onto R to the n is called a vector field, or sometimes an n-dimensional vector field if you want to stress the dimension over D. And in contrast to that, if you want to stress the difference, a function that just maps to R is sometimes referred to as a scalar field. In contrast, a function f that maps D to R, dimension 1, just the real numbers, is sometimes called again, sometimes n-dimensional to stress the dimension of D, scalar field. And to stress that once again, it's important that the dimension of the domain and the dimension of the codomain is the same for a vector field. So mappings that go, for example, from R2 to R3, you would usually not call those vector fields. Okay, finally, let's talk about visualization of a vector field and look at some examples of vector fields, of course. So how do you visualize a vector field? Well, what you can, of course, do is you can just take points in the domain, in the plane, in space, and you can draw the images of those points anchored at the points. To get an idea of how a vector field behaves, you would usually choose some kind of regular grid in R2 or in R3 or whatever dimension you have, and draw vectors anchored at all the points in the grid so that you get an idea of the behavior of the vector field. Okay, so visualizing a vector field. What you do here is, for points xi in the domain D, usually a regular grid draw the vectors v of xi anchored at xi for all points chosen. So that is a pretty simple idea, and I'm going to show you how that looks for a couple of examples. So one possible example, and probably one of the easiest vector fields that you can get, would be a constant vector field. So let's look at that first. I'll usually do the examples in the plane because that's easiest to draw. The same, of course, works in a 3D space as well. And theoretically, you could also apply that same method to n-dimensional spaces with higher n. But of course, that's nothing that you would readily draw on a sheet of paper. Okay, so the vector fields that I'm going to look at are usually going to be defined on R2 and mapped to R2. So we have a vector field v. V is defined as just the vector 1, 1 for every point. So that is a constant vector field. And the visualization of such a constant field, that we just draw the coordinate system here, x1 and x2 axis. And then we simply draw this vector 1, 1 to each of the points here. Basically, we're going to choose some kind of a regular grid. We can draw that. So that is how that visualization of that vector field would look like. Okay, so that's the constant vector field 1, 1. Okay, in contrast to that, imagine something like a central force field. Now, a central force field could, for example, be a field where a force is kind of directed towards or away from a center. So, for example, in two-dimensional space, you could again have something like a mapping from R2 to R2. And let's say we have a force that will be directed at the center. Then that means we'll have a vector field that assigns to each point x1, x2 something like a vector minus x1 minus x2. So it's directed back to the origin. And then we also want to modify the length a little, and let's say we have a force that gets weaker and weaker as we move away from the origin. So, for example, we could have a force that decreases with the square of the radius, of the distance from the origin. So that would be something like times 1 over the norm of x squared. And of course, to make that thing comparable, you would not use the vector x itself for the vector field, but you would use the normalized version of that vector, so that you don't have the opposite effect of the force increasing as you get further and further away from the center, because the length of the vectors just increases, right? So you want something like this, meaning basically you have a mapping that looks like this. And of course you can modify that through constants, yeah? An example for this would be the gravitational field of some point mass. How would that look like? Basically what you have here is a field where every vector points back at the origin, and the length of the vectors decreases as you get further away from the origin. So we have something like this. Here we have a vector pointing to the origin. As we get farther away, those vectors become smaller and smaller. And that is the same from all directions. Right, so basically that's how such a central force field could look like. One other example that I would like to mention here, a rotational field. So part 3. In rotational field, sometimes you have a field that models some kind of rotation. For example, imagine you want to model how the water behaves when it goes through a sink, so an opening. It usually starts rotating there. And of course, the speed of rotation might also be different depending on how far you are from the origin, or it might be constant, depending on the forces that act there. So one possible example of such a rotational field is something like, again in the plane, v of x1, x2 is, let's say, minus x2 and x1. So that rotational field basically behaves like this. So at the origin, of course, that vector field vanishes, just becomes a point 0. As you move away from the origin, the length of the vectors increases, because it's always the length of the original vector, so distance from the origin. So that means around a circle around the origin, the length of the vectors always stays the same. And they are rotated. Basically, what happens here is this vector here, minus x2, x1, that is perpendicular to the input vector, x1, x2. So that means the vector field has a direction that is perpendicular to the original point. So for example, if we have this point here, then the vector field will point in that direction. And so that basically means it's going to move along the circle here. And the same is true for other distances from the origin, but the vectors will get longer. So if you move to this point, for example, you get something like that. Okay, so basically it circles around the origin. That describes a rotation. And finally, one of the most important examples of vector field that we are going to investigate in more detail in later videos are so-called gradient fields. So if you have a scalar field, let's say a function capital F, defined on Rn, a mapping to R, let that be a scalar field, and say it's differentiable. Then it does have a gradient, and that gradient, for every point in the domain, that gradient is a vector. So we can interpret the mapping that maps to each point, the gradient of f at that point. We can interpret that as a vector field. And vector fields like this are called gradient fields. So we can define a vector field v, Rn to Rn, defined as v of x is the gradient of capital F at x. That is a vector field. Called the gradient field of capital F. And as I said, these gradient fields will play a prominent role. For the notation, we usually don't use the nabla symbol anymore. What we usually do is we write v as gradient of f, like this. Yeah, it means the same thing. Gradient and nabla operator, the same thing here. It's just more common to write vector fields using this grad symbol instead of the nabla operator. Okay, so grad f is the mapping that assigns to each point the gradient of a function f at that point. To round that off, let's see one possible example. So let's say we have a scalar field that is defined as f of x1, x2 equals x1 squared plus x2 squared. Then the gradient field for that gradient f of x1, x2. That is simply the gradient of f at the point x1, x2, and that is 2x1, 2x2. Okay, so pretty simple. It's just 2x, basically. How does that look like? Quick sketch. In the plane, you know, we can visualize the function f itself through its level sets. So we're going to do just that. The level set of that function are just circles around the origin. So we have a circle like that. And then let's say a circle like that. That should be sufficient for the illustration. And then you remember the gradients of a function always point into the direction of steepest ascent locally. And that means they are perpendicular locally to the level sets. So what we get here as gradients, that is functions like this here. Yeah, so they're pointing upward because a function increases as it moves away from the origin. So this is the gradient field of that blue function. Okay, so that is the gradient set, the gradient field of a function. And the orange one, those are the level sets of the function f. Okay, so that is how a gradient field looks like. And in the upcoming videos, we are going to talk about integration over vector fields in general, and we're also going to talk about the very special role that gradient fields play in this context. I'll see you then.